think we're ready to go. Yes. Okay, hold on. I probably will. Okay, hold on. Let's see here. Thanks. And, all right. What's up? What are your questions?
Yeah, so my question is,
Okay. Yes. Yes. When I say across groups, it means like they've got like math 1, 2, 3, reading 1, 2, 3, right? So it's going to be math 1 is equal for boys and girls.
Yes.
Math 2 is equal for boys and girls. Math 3 is equal for boys and girls. Math 1, 2, and 3 are not equal to each other. Right? Equal across groups. Yeah, so you're constraining the error variances to be equal across groups. Just like we constrained intercepts to be equal across groups, and we could constrain loadings to be equal across groups. So it's a cross group constraint. Yeah. Yeah. It depends. Well, it depends in the sense that, okay, if you put something in there and you don't put any kind of constraint, right, then it is gonna, so if you say like, whatever it is you say, if you say like the error variances, if you just mention the error variance for math 1 and you mention it, well, that's not going to be constrained anyway, right? So, I mean, this is the thing. So first there are these defaults of things that are constrained or not constrained, right? So by default, M plus is going to build a scalar model, which means if you don't have anything in group female, it's going to constrain the intercepts to be equal across the groups. It's going to constrain the loadings to be equal across the groups. And it's going to, but not the error variances. That's right. The intercepts, the loadings, but not the error variances. So it goes through scalar. And remember, error variances was like step 4. So that's not going to be constrained by default. So one strategy that we use with that model female is exactly what you were just saying, that if we want something that's constrained by default to not be constrained, we can simply mention it in that group female, right? So if I wanted an intercept not to be constrained, all I have to do is like put, in the little brackets, I would put like, math 1 in the brackets, right, under female. And then that would, if it's all, that would say, okay, don't constrain the intercept for female across the two groups, right? But now, like, errors are not constrained by default. So you don't need to put them in that second statement to get them to not be constrained because they're already not constrained, right? So that's why I said, like, it depends, right? So when you want to put something about the error variances into that second grouping thing is when you want to constrain it, but what you're going to do there is you're going to use the same strategy that we've used when we wanted to constrain things before. Remember, we can put in parentheses with like a number or a letter or a word. So in that case, if we want to constrain error variances to be equal across groups, like let's say we want to constrain the error variance for math 1 to be equal across the groups, then we're going to say, well, it's math 1's already up here, let's say in the full model, and then we're going to put math 1 in the second model, and then we're going to give it the same number or letter or word, which tells it to be constrained across groups. So in the model, in like the original model, let's say, before you want to constrain error variances to be equal across groups, you don't have to say anything about those error variances. You could mention the error variances in the original code or not mention the error variances in the original code. And it's not going to matter because by default, M plus is not going to constrain them to be equal. But as soon as you want to constrain the error variances to be equal, you are going to have to mention those error variances in both sections of your code. First, up here in the like main part, and give it a number or a letter or a word. And then second, down in the subgroup part and give it the same letter or number or word. Yeah? Yeah. And then you didn't say it in the model female section. Okay. Well, if that works, that's fine. I can't think of why there would be a particular recommendation to do that over the other way, but yeah, you can show me later. But I mean, that's interesting. So and again, I mean, there's always this thing with like M plus and the default, which sometimes change, by the way. So you always know whether you're doing it right or not when you check the output, right? Because the surefire way to know, have you constrained the error variances to be across the two groups, is to go into the output and see if you're getting the exact same numbers for the error variances across the two groups, right? And so like, if you did that and it works and you don't have to put it in the model female statement, great, right? If you're getting the same error variances and they're constrained, you're getting the right degrees of freedom, that's great, but you should understand the process well enough to be able to kind of figure out whether you're getting what you need to get, right? Whether you're getting these, like you should be kind of knowing whether you're getting the constraints that you want once you run it. Yeah. Next question. Yeah. I don't even know what question you're referring to, so I can't answer that. I also don't have memorized what 2D is. So can you? Yeah, so then you don't have to, then that's what you should constrain. So the difference between 2D and the model before it is that you're constraining the measurement errors to be equal across the groups, right? There's nothing in there. I don't think, if I remember correctly, I don't think there's anything in the homework that asks you to deliberately constrain does it? Ask you to constrain the means to be equal across the groups? Yeah, so no. So yeah, so all you have to do is constrain the measurement errors to be equal across the groups, not equal to each other within group though. That's an important distinction, right? Okay. Sure. Other questions? Does that make sense? Actually, after we go through this class, all of this will probably make even more sense because we're doing multiple group structural equation modeling today. So we're going to sort of pick up where we left off last time and talk about how we can do constraints, in the structural part of the model. But after today, you will have gotten like a double dose of M plus constraints. So, and in fact, I think you'll see the code in here that's very similar to the kind of code that you would be using for your homework. So, all right. Yeah? Yes. Sure. If they're not nested, you can't do a chi-square difference test. That's right. But you could still, just because you don't have nested models doesn't mean that you can't make some sort of a decision about what models are better or worse, right? So it is true that you can't make a decision about which model to pick with a chi-square difference test if you're comparing two non-nested models, but you could have two non-nested models and still have an opinion about which model you think is better, right? Mm. And this is really hard because I just don't remember off the top of my head even how model. Can you read me question 6? What does it say? Yeah, I mean, in my mind, I do think you would have some chi-square difference test there probably, but you might not all the models are nested, so perhaps, so that means that you might not have chi-square difference tests among you're not going to have chi-square difference tests for models that aren't nested. But that doesn't mean that just because there might be a model that's not nested out of a whole group of models, that you completely abandon chi-square difference testing for everything else, right? Does that make sense? And I think in the extra credit, I asked you which models are nested and not nested, right? No, you don't have to. Just tell me which ones are nested and not nested. All right. Any other questions about homework? People always get really freaked out by multiple groups, so there's a lot going on in the multiple groups models. But once you get through multiple groups models, then you'll feel like, okay, if I can do this, I can do just about anything. Maybe. Oh, I hope. How about that? I hope that's how you'll feel. All right. So today we're going to talk about moderation in SEM. So we're going to start with multiple groups SEM. And now just as a refresher, last week we talked about multiple groups measurement models. So we're kind of going to pick up where we left off last week. And so we're going to make the assumption that, just like we talked about I don't know, it's been several weeks ago now, that like before you're looking at your hybrid structural model, you're always going to look at the fit of your measurement model, right? So the same thing is true here. Before you fit a multiple group structural equation model, you're always going to start with the multiple groups measurement model, which is what we talked about last time. So I'm going to assume for this that, okay, we've done that work, right? We've done that work. We've fit our measurement model. We've done all the measurement and variance stuff for the measurement model, and we feel good about that. Now, how do we move forward and think about testing a variety of, again, it's sort of a taxonomy of multiple group structural equation models. What does that all mean? And we will actually run through and talk about at least 7 different multiple group structural equation models today. Sort of in a sort of a logical list that I hope it'll be a logical list that will make sense to you. And then, so we'll talk about multiple groups SEM first. We'll do our M+ example. And then after that, we'll talk about other ways that you can test for moderation in SEM. And this becomes, again, especially useful if you have continuous variables. We won't have a ton of time to go into a ton of detail on this, so we'll just sort of scratch the surface. There's lots more we could say about this if we had more time, but we'll just sort of do a general overview for thinking about latent moderation in SEM, and that will definitely take us to the end of class. So that's the plan for today. Did everybody get a set of PowerPoints? Okay. There are also output, but they're still printing, so there are some up here, but not enough. So I'll go, Jocelyn or actually probably Jocelyn will go down in a few minutes and pick up the rest of them. So don't worry if you don't have the output packet yet. We'll make sure everybody gets one before we start with the M+ stuff. It's a really, really, really thick packet, so I underestimated how long it would take to actually copy it. And I was standing down there for a little while, and like one came out, and then I was like, oh, this is not. All right, so, well, we talked about the title. Okay, so, Ethan, can you hear me, by the way? Yeah? Oh, that's because you're muted. Yeah, well, that's okay. Oh,
Can you hear me?
Oh, I can. You're coming right out of some big speaker in the ceiling, so that's good. I can hear you really well.
I'm like Big Brother.
Yeah, you are kind of like Big Brother. Yeah, that's pretty cool. All right, so good. So you can hear us and we can hear you, and you can see the slides.
Yes.
Okay, yeah, don't be shy. I don't want to make that mistake again. Okay. All right. So again, just to remind ourselves, last week we talked about measurement and variance, right? Where we're really thinking, are we measuring the same thing across groups? Are we assessing the same construct in the same ways? And, just to kind of remind ourselves that there is this thing called partial measurement and variance, where we find that some of our parameters are allowed to vary across groups, but others don't. So for example, maybe I can't constrain all of my measurement loadings to vary. I can't constrain all of my measurement loadings to be equal across groups, but if I can constrain most of them to be equal across groups, that's what's referred to as partial measurement and variance. There's a lot of, I think this is an area where sort of reasonable people disagree about how much variability across two groups is too much, right? So how many things need to be invariant before you're sort of comfortable moving forward? So sort of an area where there continues to be active research. Yeah. Yeah, that's right. So if you found that you had a completely non-invariant model, right, then it doesn't make sense to compare the two groups because the measures are not functioning. Like your measurement model doesn't function the same way. So how can it make sense to compare the two groups when the measurement model isn't even really, functioning in the same way across the two groups? So it's sort of this big caution for you, but yeah, it does actually put up a roadblock, which is why people are very loath to completely throw out a model if there are like just one or two non-invariant items, right? If only one or two items are not working, people sort of don't want to have to stop their entire line of research right there before they get to the structural model, and understandably so. And as we said, oh, you didn't bus, did you? Oh, I just started teaching. Can you call Dad? And if Dad can't pick you up, you're gonna have to Uber to school, okay? So call Dad, and if Dad can't come and get you, Dad will call you an Uber, all right? Bye. So as far as because they don't start school until 10 o'clock on Wednesdays at E.O. Smith, which is also of course, as it turns out, I drop her off at school every day but Wednesday, but I can't because she starts at 10. And I've been waiting for this all semester, the 9:30 call that's like, yeah, I knew she was going to tell me she missed the bus. She did. For her. Well, I can't ignore that one because I'm sure she would love to sit at home all day. All right. Yeah, maybe I'll just bring her in from now on and make her walk over to EO from here. That would be mean though, because I always come in at 5 o'clock on Wednesdays to get ready. I don't think she'd like that. All right. Anyway. So yeah. So partial measurement and variance, right? So people are kind of don't want to necessarily have to throw out their entire model just because there are one or two items that aren't working well. Which again, as we said, one option could be throw out the item, right? And if you have tons of items, especially if you're in the validation stage of an instrument, that's exactly what you would do. You'd be like, hey, this item doesn't work the same way across the two groups. So a lot of times that's what testing companies do. They test for measurement and variance. They find items that don't hold, and they throw those items out and they just don't use them. Just like with us, with bracelet and slumber, we weren't like, oh, we'll just use a partial measurement and variance. We're like, it was a pilot study. And we're like, oh, those were bad words to choose. Let's choose different words. But of course, sometimes you don't have that flexibility. It's your dissertation. You don't have a ton of measures. and you find out that one of your measures is non-invariant, but it's like conceptually really important, right? And then you have to make a case that you've got partial measurement invariance. Yes, Katie. Oh, that's okay. You can go and then Katie go. And it was really weird. I didn't realize at first that you were talking because everybody's got masks on, but go ahead. When you say non-significant chi-square, are you talking about non-significant chi-square difference? Yeah. I mean, I don't know, right? Oh, yeah. If metric works but scalar doesn't, then you dig in and you find out why scalar didn't, right? Because if metric works and scalar doesn't, that's still bad. That's saying I mean, think about what that means. That means that, okay, yeah, the relationship, sort of the strength of the relationship between the factor and the item is the same across, for all these items, is the same across the two groups. So those slopes are the same across the two groups. But after controlling for, the factor, the two groups differ in terms of their item means, right? Because that's really what the intercept is. So that means that so let's go back to my example with bracelet and slumber, okay? So if the loadings were the same, but the intercepts differ, then that means that the vocabulary knowledge is equally predictive of your response for boys and girls, but the girls just do way better on this item. Okay, so that's better, obviously, than the item is not equal, or the factor's not equally predictive of the item, and boys and girls also, score differently on the item after controlling for the factor. But it's still really not good, right? Because what you're saying is that, boys and girls of equal ability score differently on this item that I've got on my, right, that is part of this construct. Now, it turns out, so here's the thing. If you can get to partial measurement invariance, you're in much better shape if you allow the items that are non-invariant to literally have different intercepts across the two groups, because that model is saying, okay, most of these items function the same way across the two groups, but we have these couple of items where, like, we have this item where girls really do score higher than boys, even at factor mean, and you're explicitly modeling the fact that you're allowing girls and boys to have different scores on that item after controlling for the factor. So that's like way better than not checking and just assuming that the item scores would be the same after controlling for the factor. But it's not as good as being able to actually say that boys and girls, like they do, that this item does function the same way in terms of loadings and intercepts. Do you know what I'm saying? So like, it's, this is where it's tricky, because so in the ideal world, you absolutely want to be able to get to complete measurement invariance. You can't get to complete measurement invariance and you have, just a small percentage of items that are problematic, then your best bet is to allow them to freely vary across the two groups. And to say I have a partial invariant, I have a partial measurement invariant. My model is a model of partial measurement invariance. And, there are a lot of people who would say, well, as long as you can get to partial measurement invariance and you allow those items that differ to vary across the two groups, then you could move forward and look at the structural model. Having said that, though, you're going to report what you did. You're going to report that it's partially invariant. You're going to report which items are non-invariant or which subscales are non-invariant. And then you're going to let the reader make an inference for themselves whether they think that's okay or not, right? And when you get past a certain point, it's just too many. Like, again, you got 10 items and one is not, one is problematic and for some reason you feel like you can't, you don't want to or can't throw that one out, that's certainly, again, it's not as good as if all 10 are good, but it's certainly way better than if 5 are problematic, right? And at a certain point, I think everybody would say, you better be able to impose equality constraints across the majority of your items, right? So and again, I think, again, this is where people might quibble. I think if you can't do it for a majority of your items, you're sunk. But some people might say, well, it should be 3/4 of your items, whereas other people might say it needs to be at least half of your items. And some people might say, hey, you should really only have 1 or 2 non-invariant items. So in the world of partial measurement invariance, I think there's a lot of, again, this is an area where I think there's a lot of research going on, and you will find conflicting advice about how much non-invariance is too much. So our goal is, let's have none, right? If we have some, we want it to be a small amount. We want to move forward with the structural model, not imposing constraints where we can't, right? Because we'll get a better, we will get a better picture of what's going on if we allow those groups to be different on the items on which they're different. And then we're going to report that we didn't get to full measurement invariance, we got to partial. This is why. These are the items or the subscales or the variables that were problematic. And then we let the reader infer for themselves whether they think, right, that you've sort of crossed a line to a point where they don't trust it, right? And different people will potentially feel differently about that. So you're always rooting for full invariance, right? But I'm going to tell you that it's, in the real world, it is not uncommon to find yourself not in that situation. And honestly, as I said, we talked about constraining the error variances to be equal, and that's great if you can get there. But honestly, again, I'm not talking about testing companies here who are doing this professionally. I'm talking about researchers who are using, more like researcher-developed measures or whatever. Most people breathe a pretty heavy sigh of relief if they can get through scalar invariance and they have full scalar invariance. And so if it turns out that they can't actually impose invariance on every single measurement error, but they've made it through and they could constrain all the loadings to be equal across groups and all the intercepts to be equal across groups, but the measurement error variances are a little different across the groups, again, most people are like, I'll take it. That's a win, right? So again, if you can get there and you can constrain all the error variances to be equal, all the better. But, in the real world with the researcher, the kinds of measures that we often use in the social sciences that aren't, again, professionally developed. And I think our expectations are and should be higher for things where you're paying money for these instruments, right? If you're using a standardized achievement test or an IQ test or something like that, we expect those test developers are spending a lot of money developing these tests. The onus is on them to get to a place where, right, to get to a really clean spot. But some researcher developed measure, it's not surprising that things aren't always as rosy as you might hope, especially because often people haven't done a lot of this work when they're first developing the instrument. So somebody develops the instrument, they don't do this, then somebody else comes along and says, I want to use it to compare 2 groups, I'm going to do this work, and then they're like, ooh, it doesn't look so good. Yes, Katie. So, okay, so I think that's a really good question, and that's just a huge problem in general, right? But I mean, I think what guides you in terms of the invariance study is which variables do you want to compare across the groups? What are your conceptual substance, not just your control variables necessarily, but what variables are you actually interested in studying? Those variables that if I'm doing this whole thing because I want to know if boys or girls are different in terms of their whatever, that's my research question, then I need to establish measurement invariance across genders. If I am doing some sort of a study and I happen to have boys and girls in my sample, but nothing in my study is about gender, then I think it's, less important. I mean, because you're right, you could theoretically, there are, sort of almost an infinite number of variables in the world that you could think about looking at invariance across. But I think the ones that you really need to establish invariance for are the ones that you're using as the variables of interest in your structural, the variables that you're interested in. Like, these are the variables you're writing the paper, right? You're doing multiple group SEM because you wanted to know, are boys and girls different in terms of the way that these, motivation and self-concept, are the pathways from motivation to achievement, do those look similar for boys and girls? Like, that's my paper. I got to look at invariance across boys and girls. Do I have to look at invariance across race if that's my paper? No. And, also the other sort of tricky issue is, you might conceptually, I think we touched on this last week, you might conceptually really want to look at invariance across some variable where you just don't have enough information, right? So, like, you could say, I collected this data from UConn students, right? And before I go forward and I do my study, I want to look at invariance across race. And then you look at your sample and you discover you only have, you have 300 people in your sample and only 20 people are African American, right? And so you're sunk. I mean, you don't have enough people to look at measurement invariance across race there. So you also probably don't have enough people to really look at group differences either. So with any luck, that was not actually your substantive research question of interest, because if you've got 280, white UConn students and 20 black UConn students, I don't know what you're going to do. I mean, like, right, that's like a problematic sample from a lot of perspectives, I think. But so sometimes you can't look because you just don't have the sample size. But if it's your substantive variable of interest, then you need to make sure that you have, right, that you're going to be able to do this kind of work. So if I really want to compare sort of patterns of motivations of, African American and whatever other group I have, if I want to compare these two groups, then I better make sure that I can do that work so that I can actually establish that these measurements are functioning in the same way across those two groups before I start saying anything about how the two groups differ. Because if the measurement instrument doesn't function the same way, then you really are comparing apples and oranges, and it's not fair to say, oh, these two groups are different in terms of their motivation if the construct of motivation doesn't even function the same way across the two groups, right? That's kind of what we're getting at. So whatever group it is that you want to, whatever two groups it is you want to be talking about, those are the groups that you need to look at for measurement invariance. But, and if you're doing an instrument, if you're developing an instrument that you want other people to use, then you certainly, like, so let's say you are ETS, then you want to look at measurement invariance across these subgroups that you know are going to be salient. Like, I'm creating the SAT, I better make sure it's invariant across race and across gender and across whatever other salient demographic variables there are, because I don't want to put a test out there that's inequitable, right? So, like, if it's a high stakes thing like that, of course, they need to look at invariance across these sort of key demographic groups. But for you, it's really going to be the groups you're interested in. All right. Does that make sense? And, okay, just do one more thing and then I'll let it go. We live in a time where, I mean, groups are becoming less distinct, right? I was thinking about this gender example, right? I mean, my gender example is male, female, but that's so not the 2020s, right? I mean, of course, so that's important. Makes it hard, I think, to do that kind of, right? Because, again, you have a sample and you've got 500 people and you've got, 480 who self-identify as male or female and 20 who self-identify as non-binary. again, you're going to be stuck in this place where you're not actually going to have the big enough sample size to do that work. So, it's a challenge. I mean, I think this is a challenge for us. Intersectionality is super important, but it represents, I think, an analytic challenge. I feel like as a methodologist, I'm always fighting this battle between like wanting my models to represent reality in the sort of best way possible, and then also recognizing sort of the limitations that are inherent in sort of having a model get so complex, like not having a model get so complex, or sort of taking a grouping variable and grouping it out into a way that is so complex that it now becomes not even possible. Like, race, ethnicity. I mean, again, you could imagine, trying to group people into like 4 different buckets is really coarse and probably unfair. But, how many buckets should there be? And if there are 57 buckets, you're never going to be able to do any invariance studies because you're not going to have enough. So like there's always this, I feel like there's this big, huge trade-off, not trade-off, but tension between sort of parsimony and simplicity, right? And sort of verisimilitude, right? Which really is complexity. And so we struggle with this. We struggle with this in our models all the time, but I think we also have to struggle with it in terms of the way we think about groups and we think about variables. I don't know what the solution is, by the way, for some of this, but I think there's some interesting methodological work that's going on to think about some of these things. In fact, one of my former doc students and I are writing about using something called the alignment method, which is a way to sort of deal with grouping when you have smaller groups. It's like you can't do this measurement and variance work. You don't have so many clusters that you can have a multi-level framework with a random effects, but you have way too many sort of groups to be able to just kind of conceive of it this way. And actually, so this alignment method is something you can do in M+, and we're writing a paper about using the alignment method to sort of to investigate intersectionality. So, I mean, I think like this is an area I think that's really ripe for research. I can tell you it's important. I can't tell you I have all the answers right now. I don't think anybody does, but it's an area that we need to keep thinking about and pressing forward on. And you had a question? Oh, for sure. I totally agree with you. Yeah. Yes. Yeah. No, I completely 100% agree with you on that. And I think somehow the deeper we get into academia, somehow the further cut off, like probably the worse we probably get at that in some ways. Yeah, no, I totally 100% agree. So, I mean, so these are issues that we've got to think about, we've got to struggle with. None of the SEM techniques that I'm teaching you this week are going to solve these larger problems that we're talking about, larger research. But, okay. All right, so on from slide 2. So, okay, so what are some issues to think about as we move into this multiple group SEM stuff? I mean, this is true for a multiple group CFA as well. So again, we're substantially increasing the complexity of our models, right? Because we are now estimating, we're allowing parameters to vary across groups, right? And that also affects the interpretation of our model. And then, again, that also, we were sort of talking we sort of talked around this tiny bit just a minute ago, but like this also then opens up to, so also how, how problematic are some of these things, right? So there's how do I interpret this? I can tell you how to interpret any problem. I can tell you how to interpret any parameters that we're talking about. But like, how problematic should I see this as being is more of an evaluative thing, which is not necessarily the same as Like, so for example, I can tell you how to interpret if your residual variance for a variable differs across groups. That's different from saying, how concerned should you be about the fact that your residual variance differs across the two groups, right? In some sense, only the substantive researcher can truly, totally answer that question. The methodologist can say, this is what it means, right? But depending on what your research study is, what you're doing, how non-invariant, I mean, there are all these things. What's the degree of non-invariance? What are you trying to accomplish in your study? Et cetera, et cetera. Like, you know, so maybe there are times when I don't, you know, in some research scenario, I might not care that I have a residual variance that's a little different across two groups. But in another research scenario, that might be critical, right? This might be really a big deal. So, you know, as you're going to see from our packet today, you know, we're going to end up with a lot more output, just a lot more stuff to wade through, right? Because we've got multiple, you know, basically getting separate, I mean, they're simultaneous, but we're getting, you know, sort of all parameters for all groups. Everything I'm doing in this class is comparing two groups. But as you can imagine, if you're comparing three groups, it gets just that much more complex, right? Because now you've got, just imagine, let's say we've got black, white, Latinx, right? So now it's, is there a difference between black and white? Is there a difference between black and Latinx? Is there a difference between white and Latinx, right? So now three groups, there are literally like three potential comparisons. Four groups, there are even more comparisons. And so, you know, again, at a certain point, you almost, you know, think about type 1 error rate even, right? Like at a certain point, if you have that many groups and you're making that many comparisons, you're going to hit something that is not going to be the same across groups. So, you know, there's a lot to think about there. We certainly need larger sample sizes when we're doing this work because we're essentially really fitting the model separately in the, I mean, again, when I say separately, I don't mean that literally because this is a simultaneous model, right? We're actually modeling the whole thing simultaneously, but we are estimating separate parameters for each of our groups. So, you know, you can't have 20 people in a group and estimate a whole nother set of, you know, and estimate 30 separate parameters for a group of 20. Nor should you probably estimate 30 separate parameters for a group of 40, even though you could potentially do it. It's still probably not a great idea. And again, we need to really start out with a model that, we need to start with, you know, we would like to start out with a model that fits well, right? So our sort of initial model, that first model that we fit where we're not imposing any constraints and we just have I mean, again, we start with a measurement model, really. You know, if that doesn't fit well, even before we can make constraints, then we're kind of sunk, you know? Yeah. Yeah. So it really depends. I mean, I think it depends on your paper. I think it depends on the journal. I think it depends on the field, instruments you're using. I mean, I think it really, but for sure, I would say minimally, you might not be able to get all of this into the paper, but it should be online somewhere and laid out in the way that we have it, right? I feel like often what ends up happening is the paper might really only talk about the structural model, and it might just sort of make reference to the fact that we first did all this measurement and variance testing. See the online appendix for more info. Yeah, see supplementary appendix for this information. For sure, it has to be documented. It should be publicly available to everybody else to see. But, you know, page space is at a premium in journals. So if your real focus is on the structural model, it wouldn't be uncommon for, even if you put it in to the original paper, you know, it wouldn't be uncommon for the editor after it goes through review to be like, you know, you can just take that whole first part and put it in an online appendix. Oh, in dissertation space, you are unlimited. You should have all of it. Yeah. Yeah, especially if like you have somebody like me on your dissertation committee. Yeah, for dissertation for sure. And, I find myself, again, I find myself sort of using a little bit of a different model these days when I write up research papers, especially like when they're, sort of larger research studies, which I didn't totally understand when I was, I didn't used to do this when I was sort of more junior, but which is sort of like this white paper. Like I'm gonna write this really, like, we're gonna write a tome here. We're gonna, like, I've got to have this document that actually has all the stuff we've done, right? Everything we've done, again, in a logical order and everything, knowing full well that at the end of the day, this 75-page document that has all of the preliminary descriptive statistics, all of this stuff, that is never going to be what I said. So it almost is like kind of creating little mini dissertations for myself, right? But once you write your dissertation, you'll find yourself sometimes like referring back to it, right? Because it is just such a corpus. It's so exhaustive, right? And, I think sometimes when you just try to write targeting like the 15-page, space that you have for an article, you end up, you end up not having the whole story there. And then when you send it out for review, people want to know, well, what about this and what about that? And you're like, well, I did check that, but I didn't put it in the paper because, or whatever. So I've just sort of started to make an exhaustive thing, and then those things can just be carved out and put online, right? Yeah, exactly, like a lab notebook, exactly like a lab notebook. But all that stuff can be shared publicly. And I think, again, that's what, with open science, that's the kind of stuff we should be doing. We should be documenting our process. That should be available to everybody. That 75 pages is never going to make it into an article, but it certainly can be made available to people who want to know what the process is. And then that allows them to kind of make a better decision about if what you said in the 15 pages that you described, which will never contain every single detail possible, whether they should sort of trust that or not, right? Does that make sense? All right. But of course, when you're doing multiple group stuff, 75 pages won't even be close to enough because, as you'll see, our output for today is 61 pages. Yes. Oh yeah, why don't you go get the output before, because we might get to it before the break. No, it's only, I've got half of it up here already. It'll be okay. So, so we want a model that fits well to start, right? I mean, if we have a horrible model, we're kind of sunk. I remember many moons ago, I was writing a paper with another faculty member, and we were looking at, there was this instrument that was published in ARJ, which is a good journal, or, the sort of the bones of it was made reference to there. It was a researcher developed thing. And they said that it was that it measured one single thing, collective self-efficacy. And it really, a two-factor model fits so much better than a one-factor model. When you looked at the items, you could see these are two different things. They really are. It was so obvious. But you know what? Like, even the two-factor model had a horrible fit. So it fit way better than the one-factor model, but the fit was still incredibly lousy, right? And so when we submitted this paper for publication, what came back was like, well, both models are dogs. So why should we care? Why should we publish this? To which, the answer was, well, because people are using this instrument as a one-factor. It's a lousy instrument, and they're using it as a one-factor instrument, right? So, like, you should publish this. It never did get published, actually, in that format for that reason. So anyway. All right. I think we talked about, no, we didn't talk about mimic models last time. It's here. So there are simpler ways. Then this is important because sometimes you don't have a big enough sample size, as we've talked about, to actually do a full-on multiple group model, right? So there's a sort of a simpler way to look at invariance, but you won't get everything out of a mimic model that you get from your, from a measurement, like a multiple groups model. So I thought I had, here we go. Oh yeah, I should have taken this slide out here. I put the picture on to this week and forgot to take out the non-pictured one. Okay, so here's what a mimic model looks like. So in the corner there, you can see that gender is, let's say, our grouping variable, okay? And let's say that we're looking at reading ability, that's our latent variable. So we just have one latent variable here. And instead of fitting a, remember before we were fitting this multiple groups model, right? Where we were literally fitting, sort of simultaneously fitting the same model across two groups. What we're doing here in a mimic model is saying, okay, gender, I think, is going to predict reading ability. And I also, but before I just say, is there a difference between genders in terms of reading ability, which I've made a case that we should not just go there, right? So I'm going to allow gender to predict reading ability, and reading ability is going to predict all of these items. And then gender also has a direct effect on each item. And what that is really, if you think about that, that's like a partial regression coefficient. It's the effect of gender on the item after controlling for ability, right? And so what do you think I would like to see there? Yeah, exactly. I would like those to be not statistically significant on the item after control. So this is another way that you can look at invariance when you don't actually have a big enough sample size to go full on multiple groups. Because the sample size requirements for something like a mimic model, especially like, if one of the groups is much smaller than the other, are far less they're not as sort of stringent. But here's the thing. So what I'm really getting when I do this is a test of whether the intercepts are different across the two groups. So when I allow for those blue paths there, those direct effects of gender on the item after controlling for ability, that really is like allowing the intercept, which remember is like the score on the item after controlling for ability. It's like allowing the intercept to vary across the two groups, right? So if I find a path from gender to item 3, and let's say it's positive, that's saying whatever, let's say gender's scored 0, 1 in this case. So gender 1 has an intercept that's that much, that's 0.2 points higher, let's say, than the intercept of gender 0. So these paths are really like testing differences in the intercepts. There's no way, though, in a mimic model to look at differences in the loadings. Or in the error variances for that matter. But I think, the more important thing that we can't look at, I could live with the no error variances more easily than the no loadings. There's no way, in this model, we're assuming, if you think about it, those black paths are really like how does reading ability predict, how does reading ability predict the item score, right? And again, sort of in one group, but then we get this we potentially get a gender effect, but that's really actually that's really bumping the intercept. It's not affecting the slope. So we're really making an assumption that the items are equally predictive, or the factor is equally predictive of the item or of the subscale across the two groups. And so that's the downside of using a mimic model. So sometimes, you can't test equality of factor loadings, you can't test equality of, variances and covariances, or error variances and covariances. But you can use mimic models with, for smaller sample sizes. So sometimes this is really going to be your best bet. And also you can use mimic models with continuous variables. So I gave the example there of gender, but that gender could be SES, and you could use it as a continuous variable. And so that is actually an advantage, right? If you have a continuous variable, then you sort of have to weigh the pros and cons of Do I slice up my continuous variable into a dichotomous or a trichotomous variable and do multiple groups, in which case I get some interesting stuff, but I'm also losing a lot of information about the continuity of the variable? Or do I use my SES variable in a mimic model where, okay, I'm going to have to assume that the loadings, I can't, it kind of makes sense. If it's continuous, of course, I can't really test equality of loadings for a continuous variable, but so again, there are sort of pros and cons to these approaches. Yeah. Oh, I don't think it's a plan B if you don't pass metric and scalar. I think it's a plan B if you don't have the sample size requirements. So to go back to my example, let's say I've got 500 people, but only 50 of them are in group A and 450 of them are in group B. And I really want to look at invariance, but there is no way I can do a full multiple groups model with 50 in this group and 450 in this group. But what I can do is a mimic model. And in that case, by the way, you're going to want the 0 group, the reference group, to be the group that's 450, right? The larger group should be coded 0. Smaller group is going to be coded 1. And then, although I'm not going to be able to look at equality, I'm not going to be able to do everything I can do with a multiple groups model. I can at least see if these items seem to function the same way in terms of the intercept, right? Do two people, no, not two people, but you know, I always like to think of it as two people, like as my hypothetical. Do two people with the same ability score, do two people with the same, like, whatever it is, reading ability score, but from these two different groups, would they be expected to score the same way on this item? Or after controlling for ability, would I expect a person from this group to score higher on this item than the other group? Which, again, is not the whole shebang that we talked about last week, but is way better than nothing, right? So like, if you can't do a full-on multiple groups model because you only have 50 people from this one group, then you should do a mimic model. But I think it's not, you know, right up front by looking at your sample sizes, I feel like, which direction you're going to have to go. And if you've got the sample size to support it, and you've got a dichotomous variable or trichotomous variable, I would go multiple groups. But if one of your groups is really small, you know, and you can't do multiple groups, then I would go with a mimic model. No, you're not like, oh, I couldn't establish metric invariance. I'll just use a mimic model because I can't look at the equality of factor loadings there, and then nobody will ever know that I looked at them and I failed. That would be, no, that's a big no-no. That's like the reason that we have really bad reputation, right? No, that would absolutely be. So this is a decision. So actually, this is a decision you ought to be able to make probably maybe before you collect your data. Although I would say often, I hedge, because often before you collect your data, you're like, yeah, I'll have enough for multiple groups. And then you actually get your data set and you're like, oh crap, I can only do a mimic model, right? But for sure, this is a decision you should be able to make just before you ever run any models, just by looking at the number of people in the groups. You know, like you only have to like run one descriptive statistic probably to make this decision. Yeah. Or you have continuous variables. Yeah, that's the other big thing. Yeah. They do both test the equality of intercepts, but what you don't get text of the, but this model assumes equality of loadings, right? Without explicitly testing. So it is like testing a scalar model without being able to check that you've got metric equivalence first, which is why you can see why that's like not optimal, right? No, the disadvantage is that the loadings are constrained. We only have one set of loadings. So implicitly, they are constrained, right? That's what's a disadvantage. So it's not an advantage that we don't have to. The disadvantage is that we can't actually look to see if they vary, right? And then like, if for those of you who live in the land of item response theory, this is really the difference between uniform and non-uniform diff, by the way. So a mimic model is like uniform diff, right? And a multiple groups model allows you to look more at like non-uniform diff. But yeah, I mean, again, we would like to be able to test for metric invariance, right? Before we move on to, without just assuming that these, because otherwise I'm saying, going back to my example of like, what's my example of slumber and bracelet, right? So we found that the intercepts were different, but also the loadings were different. So not only did girls score higher on slumber, but it also didn't predict their vocabulary knowledge nearly as well. But when I do a mimic model, I can't capture that aspect that actually, that like, that general vocabulary knowledge is, actually predicts whether a boy knows slumber or not, but it doesn't predict whether a girl knows slumber or not. It just is going to, right, I'm only going to get one loading across the two groups, and then that has the capability of really kind of, sort of biasing or warping my picture that I see is now going to be affected by that, by making an assumption that I shouldn't be making, but I have no way to know I shouldn't be making because I can't test it. Yeah. Yeah, that's what I'm saying. So like if you could have a really large sample, but you could have a group, it could be very uneven. So one group is 400 and the other group is 50, right? And even though you have plenty, 450 sounds like that should be plenty for a multiple groups CFA, but it's not if there are only 50 in one group. That's exactly right. So if you end up with a sort of a small group, that's a very common time that you might use this model. Or if you have a continuous variable that's a covariate and you want to treat it as continuous, that's another time that you would use a mimic model. So they're not, I mean, there are times that these are good models, but if you have a variable like gender and you have enough in each group, I wouldn't do a mimic model in that case if I could do multiple groups, but there are times when mimic is your only choice. Okay. Yeah. So I already said all of this, right? All right. Now let's talk about multiple groups SEM models. So we're going back to this same old model that we used actually the measurement model for this last week. And you'll recognize this model from, I don't know, week 4 or something of class, right? We keep using the same old model. So we've got academic self-concept and goal evaluation, which are latent variables, predicting motivation, which is a latent variable. And right, then motivation predicts homework, and then homework and academic self-concept and goal evaluation all predict GPA. And this is the conceptual model. So the just identified, the conceptually omitted paths are not actually shown in this particular picture, right? But do you remember where are our conceptually deleted paths? Where do we not have paths that we would to get to a just identified model? Yeah, from what did you say? From goal and academic self-concept to homework, right? Those are 2 of them. And then from motivation, yep, from motivation to GPA. So there are 3 conceptually omitted paths in this conceptual model. The same 3 conceptually omitted paths that we've had all semester long. Okay, so this is our hybrid model. Again, we're going to assume for now, because we did do this last week, that we started with a measurement model and we dealt with, checked for measurement and variance. And you might not remember what we found last week, but if memory serves correctly, I think we got to partial scalar invariance, right? So there was like one, if I remember correctly, I think there was maybe one variable that we allowed to vary across the 2 groups. S26, that's right. Oh, and actually on our I know, that's why it took so long to print this. Go back, rather. Okay, and Ethan, this should be on the Husky, whatever it is, Blackboard site, this output, the PDF.
Yeah, I downloaded it.
Okay, great. So Yeah, so if you look on the output, actually, I have, let's see, it was S26. Oh, I'm on page 1. And I just wrote, I now know what the item is. It's I'm organized about my schoolwork is what S26 is. And that varies across the two groups. Did everybody get one of these, by the way?
Wait, sorry. Betsy, what page are we on?
Just page 1 for right now. I haven't really done anything.
Okay.
I was just saying that S26 is I am organized about my schoolwork. And if you look, the intercept for S26 is higher. So basically, after controlling for motivation, females are more likely to agree with the statement, I'm organized about my schoolwork, than males are. So basically, after controlling for this motivation latent variable, girls report being more organized than boys. Okay. But other than that, we were able to get to scalar invariance, right? Sure. Yes. Interesting. Okay. Yes. Got it. So you don't need to put the you don't need to put in the line about the intercepts being held. Yeah. Yeah, I think I discovered that myself and got rid of them. So, okay, so where it says intercepts are held equal by default, where it says, and then it has in brackets S08, S11, S13, S15, S20. If you run with that line of code, it will kick you an error message. Just the bracketed part. But you don't need that, because what I said was this is held equal by default, but then I put it in there. And so it just gets confused, which, by the way, is a change from M plus. See, this is what I mean. Like, things change. This is a change from one version of M plus to another, where it used to work. You used to be able to do this, but now you can't, because they're constrained by default, and so it doesn't want to see you put the thresholds in for one group but not the other. So if you get an error message when you're putting in lines that you don't need, don't use them. And I apologize that it's still in here. So I should make a clarification about that. Yeah, I think I discovered that last year, actually, when I was running the code from like the year before, and it suddenly was kicking me error messages, so I got rid of that. Like, why? I don't know. It used to work. Now it doesn't. Actually, I can't tell you. I mean, I've been using M plus for long enough to know that kind of stuff happens. Which is why I say you just kind of have to know the M plus defaults. You have to also know how to check stuff, because it's not very hard once you run something, to see like, oh, okay, well, that didn't work. Okay, so for your homework, I think the important thing that Fayez is saying is, for your homework, don't put in that line when you don't need it, because it might kick you an error message. And if you get an error message, that's your most likely scenario, is that you put in that line when you didn't need it. So I think that's a good tip. So I apologize, and I will take that out of the handout, which is a PDF that I created in a different version of M+. I can put a little exclamation, that's what I'll do. I'll put a little exclamation point. What I really need to do is put a little exclamation point and put a little note there that says, don't put this in your model when you don't need it, or you're going to get an error. So don't put this in your model when you don't need it, or you're going to get an error. All right. So let's go into M+. 11. open. Example. Sure that this is not this. Yep. Shouldn't need that. Okay, let's talk before we get into talk. Should have probably maybe done this before I even went into M+, but let's talk about the logic that we're going to use here for this multiple group SEM. Okay, so let's think about this. Let's think back and remember how we tested a hybrid model from the point at which we had a measurement model. Because remember, the first thing we always did with the hybrid model is we got our best measurement model. That was step one. And so that is equivalent to what we did last week, except for it was our best measurement model that was a multiple groups measurement model, right? And then remember, what did we do after we had our best measurement model when we were testing a hybrid structural model? The just identified model, right? And why did we fit the just identified model? What was the logic? I mean, we did it for a particular reason. To test the conceptually omitted paths, right? So those three paths that we think that we don't need, do we need them? So the first step was always just identified model. That's conceptually omitted paths. Right? Okay, how might this get more complicated now that we're in a multiple groups framework? Yeah, okay, because now we've got, that's right, because we've got these conceptually omitted paths potentially across the two groups. So think about how those, what could be going on? Like, it could be that this path, like, let's just take one of them, which is like, third one was are the three that we think we don't need. But in a single group, we just had like just three paths. But now we actually have, again, if we allow them to vary across groups, we have academic self-concept to homework. We have a path for boys. We have an academic self-concept to homework path for girls, right? So now you've got like ASC homework boys, AST girls. Right? And again, in a single group, we just wanted to know, is this path different from zero? But in a multiple groups framework, we're actually quite interested in, are these paths different from each other, right? So what's the logic? What's the logic that's going to make sense as we sort of go through and build these models? We're not going to just start by deleting those three paths across the two groups. That doesn't necessarily make sense. The first thing we need to know is if we want to delete the path, we really need it to be the case that we can delete that path across both groups, right? Which means we need that path to be not statistically significantly different from zero. Once we've constrained it to be equal across both groups, and we need that path to be able to be constrained to be equal across both groups. Because think about this, like if I find that this path functions differently across boys and girls, then I would want to leave it in, right? You could actually, if you think about it, where let's say this path is just a little bit positive for boys. This path is just a little bit negative for girls. And then neither of these paths are actually statistically significantly different from zero, but the paths are statistically significantly different from each other. And that actually would be information I would want to have. That would be important, right? In some sense, that's like actually more what I'm after than whether they're different, right? So with this multiple groups model, before I get rid of the conceptually omitted paths, I've got a new step. The first step is constrain the conceptually omitted paths to be equal to each other and test to see if that constraint is reasonable. Okay? So whether the omitted paths cross group, constrained across group. So in this model, when I do that, let's say, and I'm gonna run a baseline again so that I can do my chi-square difference testing, and so I have something to compare to. I'm gonna start with a baseline just identified model where all of my parameters, all of my paths are free to vary across the groups. And then the next model that I fit is gonna be a model where I say these three are constrained across the two groups. So how many degrees of freedom am I gonna pick up in model 2 then? 3, right? Model 2 will have 3 more degrees of freedom than model 1, because in model 1, I'm allowing all of the paths to vary across the two groups. And in model 2, I'm gonna see if those, if I can constrain them to be equal. If I can constrain them to be equal to each other, and then let's say I can constrain this path to be equal. Slide left. See, I should have pulled up. Yeah, look at the slides. But there we go. I'm just going to leave it like that for now. Okay, so the first model I'm going to run is this just identified or hybrid model with no constraints. So that's like my baseline model, just to get on the board. This model will have the same chi-square and degrees of freedom as the final measurement model, right? Just like when I fit the just identified model. Remember before when I fit the just identified model? So, in the single group case, my just identified model was the same as my final measurement model. So that's going to be true here, okay? So, but this is where I'm going to start out. So I'm going to fit that just identified hybrid model. I'm not imposing any constraints on any of my structural paths. I am, however, as I said, because I am imposing any of the measurement constraints that I'm taking my final measurement model. So the measurement model looks just like my final measurement model, but I'm fitting a just identified structural model, okay? And again, by default, M+ is allowing, correlations or paths or whatever to freely vary across the groups. And so that's why this model will have the same chi-square and same degrees of freedom as whatever your final measurement model was. So that's a good check too, right? Run your final measurement model. When you come over here and you run this model, you should get the same chi-square and degrees of freedom. Okay, great. Step 2 is now I'm going to take that just identified structural or hybrid model, and I'm going to constrain the deleted paths, those conceptually, omitted paths, to be equal to each other. So again, just like the same logic that we used in the single group case, I'm not looking at all of the paths yet, only the ones for the paths that I want to be able to get rid of. So we're only talking about those conceptually omitted paths, right? So just these 3 paths. First thing I do is constrain these to be equal. So this is actually going to be model 2 in our output, okay? Because model 1 is just this baseline, just identified model with no constraints. So I'm going to constrain the deleted paths to be equal to each other. See if I can do that. If I can't constrain the paths to be equal to each other, what do you think? What should I do next? Let's say I can constrain. Let's say I can't constrain the paths to be equal for academic self-concept and homework for boys and girls. What? Oh, I was going to say, well, constrain 1 to what? Constrain 1 to 0? Oh, yeah, exactly. Yes. For sure. So I got 3 of them. I'm going to see, can I do all of them? Can I do 2 of them? Can I do 1 of them, right? So I'm going to look at, can I, if I can't do all 3, could I at least do 2? For sure. But what about, let's say I can't do one of these. Let's say I can't constrain this. Then it's going to stay. Right? It's going to stay because then that's interesting because the boys or girls are different in terms. So now this is the reason that so even before and to test whether it's 0, we're going to test if it's equal across the 2 groups. And if it's not equal across the 2 groups, it stays. It's in. Okay? But if I can constrain it to be equal across the 2 groups, then I'm going to test whether I can delete, right? Once I've constrained those paths to be equal, if the constrained path is not statistically significant, that means the constrained path, which is already constrained to be equal to each other, is not statistically significantly different from 0, then I can trim that path. But I want to be able to trim the path from both groups. So first I'm going to constrain it to be equal. Then I'm going to look, can I trim that constraint? Can I get rid of that path? Is that constrained path not statistically significantly different from 0? And if it's not, I trim it. So this is where it's just a little bit different because it's like a 2-step process now. Instead of just looking at conceptually deleted paths, we really have to look at first, is this conceptually omitted path, can it be constrained to be equal across the 2 groups? If yes, now once it's constrained to be equal, can I get rid of it? If I can't constrain it to be equal, it stays. If I do constrain it to be equal, but it's statistically significant, it stays, right? It only goes if I can constrain it to be equal, and after I do that, it's also not statistically significantly different from 0. Yes, Fayez. Well, first, we're constraining them to be equal to each other. So when you constrain. Okay, well, remember, my first step is I'm going to constrain the paths to be equal to each other. So was I able to constrain the paths to be equal? Yes, okay. So I constrained the paths to be equal to each other. So now I'm only fitting one path. That path is not statistically significantly different from 0. I delete it. Well, no, because if it's constrained, it's going to be the same, right? The only way you could get a situation where it's significant in one group and it's not significant in the other group is if it's not constrained, right? That's why, this is actually exactly why we use this system, because that gets you in all kinds of trouble. So the first question is, can I constrain the path to be equal across the 2 groups? If the answer is no, I can't do that, then it stays. And what's most salient and most important there is that the path is different across the 2 groups. And you're right, if the path is different across the 2 groups, it could be the case that it's statistically significant in one group but not statistically significant in another group. But that's actually a compelling reason to keep it, right? Because that's interesting. Again, the most interesting part of that, though, isn't that it's significant in one group but not in the other. In some sense, the more salient thing is that the path is different across the 2 groups, right? So that's what we're looking at. We're looking at whether the path is different across the 2 groups. If yes, keep it. If no, is it different from 0? If it's not different across the groups and it's not different from 0, now I really can get rid of it, right? Because I can constrain it to be equal across the 2 groups. And once I do that, it's basically 0 across the 2 groups. It's giving me nothing. Out it goes. But if I can't constrain it to be equal across the 2 groups, or if once I do that, it isn't, it is statistically significant, so I can't get rid of it, then in either of those cases, it's going to stay. And in the first case, it stays and it's not constrained to be equal across the 2 groups. In the second case, it is constrained to be equal across the two groups, because we could do that, but it still remains in the model because it's constrained to be equal across the two groups, but it's just not 0 across the two groups. You see the difference? So we need to use this sort of like logical sort of model building approach where we kind of know it's like we've got a real system here for why we're doing this, how we're doing it. Otherwise, you can get into all the kinds of things that Fayez was thinking about that then get really mucky and troublesome. So when we use this system, it becomes very clear what we're doing, why we're doing it, and how to interpret it. Okay, so got it. So that takes us up to step 3. So steps 1, 2, 3 are all actually about the concept. They sort of are just the multiple groups equivalent of the conceptually deleted paths step from a single group model, right? So now we've dealt with our conceptually omitted paths by the time we get to the end of step 3, yeah. No, we're going to use chi-square difference test. Yeah, we're going to use a chi-square difference test. Just like we've been doing, yeah. So then, okay, so then the question, then we're going to do the same thing with our conceptual model, right? We've got our unconstrained conceptual model, which really, you know, which includes any additional paths after steps 1 through 3. So sort of at the end of step 3, this is where, at the end of step 3, we have this model where we've dealt with our deleted paths and we have all of our conceptual paths are not constrained. And then the next step is, can we actually constrain our conceptual paths to be equal across the two groups, right? So we'll constrain the conceptual paths to be equal across the two groups. And then remember, we talked about, you could, you know, sometimes people trim non-statistically significant conceptual paths out of the model. Sometimes people don't. But again, if you were wanting to trim non-statistically significant paths that are conceptual paths out of the model, use the same logic that we just talked about before, which is first we constrain the paths to be equal, and then we look to see if the paths are statistical. Right? And you would not trim a conceptual path out of a model unless you could constrain it to be equal and it was also not statistically significantly different from 0 after you constrained it to be equal. So yeah, so there's this optional 6 of trimming. So when we look through our models today, we're actually going to fit, we'll walk through them and you'll see, we're actually going to fit 7, I believe the way, when all said and done, because we're going to do some partial stuff too, I think we're going to fit 7 different models. All right, and then obviously, once you can explore partial invariance in terms of the measurement, not measurement, I'm sorry, in terms of the structural paths. And then finally, we haven't talked about it here, but they're also, once you've done all of this with the paths, you can then also look for, you can also then constrain means and intercepts to be equal across the groups. Because remember, these paths are really just talking about the structural relationships, like do the direct effects, right? Do these paths, are the paths equal across the groups? But you could have the same kind of, you could have the paths could be equal across the two groups, but one group could be higher than the other group in terms of their level of motivation or their level of self-concept, right? So looking at the paths doesn't tell you anything about the latent variable means or the intercepts. So the next step is actually then, after you've done, I would say, after you've done all this, is, if you're able to sort of get to a reasonable place, right, then you're going to look at the latent variable means, and then finally potentially, or the latent variable means, and also it could be the observed variable means and intercepts as well. Latent variable means and intercepts, observed variable means and intercepts, and variances. Are the variances different across the two groups, right? And then finally, you could look at it whether covariances are different across the two groups. So we'll talk about what each of those things is as we kind of go through. Does that make sense? If I wanted to say anything. Okay, so again, don't trim path, just because a group path is statistically significantly different from 0 and in one group and not another, right? You can't actually infer that the paths are different from each other. So you're always going to directly test this constraining paths to be equal to each other first before you look at whether they're different from 0. I think that's all let me just, okay. Hey, this is maybe where we should go on. So here in our example today, we're going to look at 7 structural models. The just identified model, we're going to test those 3 conceptually deleted paths. We're going to constrain them to be equal. We'll delete the conceptually omitted paths that we can constrain to be equal. Well, we'll test to see if we can delete them, right? Then we'll see if we can constrain all the conceptual paths to be equal. And then in our model 5 today, we're actually going to look at, once we've constrained all our paths to be equal, we find a conceptual path. This is the same one from way back. Goal valuation to GPA was not statistically significantly different from 0 when we were doing it in a single group model. We're going to see, can we eliminate that path? And then we're going to look at, can we constrain means and intercepts to be different across the groups? And then, yeah, time permitting, probably not. I had high hopes, but I was thinking time permitting, you could try to constrain the variances to be equal across the 2 groups. So we'll see how that goes. Maybe there will be time to do that. But that's kind of the logic. I wouldn't constrain them. I would, again, I'd do the means, intercepts, and then the variances, covariances sort of at the end, after we've sort of done the paths. Yeah? What do you think? Ready to try it? All right. Close this. All right, so here we go. Here's our first model. Paranoid.
Hey, Betsy.
Yeah.
Yeah, I'm just making sure I'm on the same output. It's MGSEM _ 2018 _ SEM1.
That is the one.
Okay.
Is the one. Actually, maybe we. Okay. You can. It doesn't really matter. It doesn't seem to be making much of a difference to me, but you can. Let's just make sure we've got the same thing on the out that we have on the output here, by the way. 104.309 with 81 degrees of freedom. Yeah. So this is the model that we want. Yeah, you don't need the thresholds. I don't know. It doesn't seem to make much of a difference. Oh, wait. Do you use a Mac? Yeah, a Mac. Okay. I was going to say, because actually in the multiple groups, there are places, I think, where M+ functions a little differently for Macs and PCs. Yes. Yeah, I have a note about that. I have a note that I reminded myself about. I don't want to mess it up. So after the break, I'll tell you what I wrote down in the note. But I actually think that is one place where I believe, yeah, if I remember correctly, I think it's about the constraining the intercepts. I don't think it necessarily, the defaults for constraining intercepts work the same way for Macs and for PCs. Yeah, here, I'm going to bracket out everything we don't need. How about that? Okay, we do need that. We really don't need this.
Data that we had last week.
Okay.
It doesn't need to be.
Okay. Well, we don't. Okay. Well, that is strange, but we don't need everything that I've just put. You don't need any of that, because everything right now here is actually going to not be constrained to be equal by default. The structural parameters in M+ are not going to be constrained to be equal by default. So. Sure. Yeah, it's really not going to matter. So, where it says, everything here has to be in the model, right? This, it's not going to matter whether you put it in or don't put it in. The variances, these are freely estimated across the two groups. You're going to see that in the output. So whether you put it in this model statement or don't put it in this model statement, they're going to be freely estimated across the two groups. The variances, the means, all the structural parameters are going to be freely estimated across the two groups. Whether you, and this is like a thing, right? You don't normally need to say anything about the variances in a single group model either, or the means in a single group model, right? They're just, or the intercepts, they're just there. So you can say something or you can not say something. It doesn't really matter. I put all this in just to kind of put the notes to say, like, to remind you that the variances are freely estimated across the two groups. And that the means of the latent variables, the means and the intercepts of the latent variables, when you have a latent variable, the means and intercepts in the reference group are going to be 0 by default, and they're going to be freely estimated in the other group. And then finally, that actually this error covariance, which I do need to have in there because otherwise it wouldn't be part of my model, that is not going to be held constant by default across the groups either. So I think what's most important here is actually just sort of the notes that I'm giving you about what the defaults are. And the only thing that is different right now is that we had a partial scalar model. So here, because M plus fits a scalar model by default with multiple groups, I want to allow the intercept for S26 to vary across the two groups. So to do that, I have to refer to S26 in the model female statement. If I don't, the intercept for S26 is going to be constrained to be equal across the two groups. So here in model female, the only thing that's here right now is just telling M plus what is different between my measurement model and a full-on scalar invariance model. And by default, all structural parameters in M plus are going to be free to vary across the groups. So when I'm going to have to tell it when I want to constrain stuff, but I don't have to tell it anything if I don't want to constrain stuff with the structural parameters. So it's like, I know this is confusing because it's kind of like the exact opposite of the measurement model, right? So like, that's why I really wish that the scalar model weren't the default model in M+. I find that to be annoying for people who are just, I mean, once you know it, it's fine. But like when you're first learning, it would be just nice if the default model were the, configural model, right? The unconstrained model, because that's exactly what happens in the structural part of the model, is that the default for the structural part of the model is that everything is unconstrained. So when you want to start off with the just identified model with all of your structural parameters being unconstrained, you have to do nothing. You don't have to worry about anything. So you just have to say your model. Like, so all I've done, if we look up here, is this just looks like a single group model. It's like, this is the exact same code. If you went back to like week 4, this is the exact same code we used in week 4 for a single group model. I just put it in the model statement, but because I say grouping is sex, right? It's going to actually run a multiple group model. Follow the logic there? Yes. So iterations, so by default, M plus runs 1,000 iterations. You probably don't, I mean, that's usually sufficient. Sometimes I find myself putting in statements about upping the number of iterations. I used to do that all the time just to be on the safe side. But generally speaking, it doesn't really matter. So you'll know if you need more iterations, you will get a message from M+ that says, no convergence, period. Number of iterations exceeded, period. And then that'll be a surefire sign to you that you need to up the number of iterations. But here's the bad news. My experience is that probably 80 to 90% of the time when you get that error message, you can up the number of iterations by a factor of 10 or 20, and it still won't solve your problem. You know, you're not getting convergence, but it's not like, oh, you let it iterate 1,000 times. If you had just gone 2,000 times, you would have been fine. Like 1,000 times is a lot of iterations. If things aren't working after 1,000 iterations, you usually have bigger problems than what. Yeah, all of these are actually by default. Well, actually, it's not totally true. It is true. It is true that the exogenous variable. So this is actually exclamation pointed out because I think it's from my measurement model. So remember, in the measurement model, all the variables were exogenous and I had correlations among them, which I really shouldn't have had to say because they would have been correlated by default. But actually here, the only correlation that would be by default would be the two exogenous variables, which are academic self-concept and goal evaluation, right? Because actually I have paths from, right? Because here I've got motivation on academic self-concept and goal evaluation. So here I definitely would want to not try to run it with those statements in the model. So let me get rid of that. Because that would do all kinds of bad things. You don't do this with your code, but I often just like mess around, and as I'm building stuff, I just exclamation point out old pieces of code. Yes, Faiz. Yes. Well, then you would actually have to, so what you would want to do is you'd have to set the intercept to be equal to 0 across the two groups, right? And then you would freely estimate the mean across the two groups. So you can just do that with M+ code. So the first thing you would do is you would, so the intercept, whatever the marker variable is, you're going to actually have to put in brackets, like, what was the marker variable? Like S11 at 0, right? And so you're constraining S11 to be constrained to be equal to 0. Then you will have to explicitly have the latent variable mean in both places so that you are explicitly modeling the latent variable mean across both groups, right? So yeah, so you can do that. You just basically have to override the default. All right. So let's take a look at our output. So first model here, we want to keep track of this, by the way. So our chi-square is 80 with 81 degrees of freedom is 104.31. We have the 3 deleted paths. That's really all we want to look at here, right? And in some sense, we don't even have to. I take that back. We don't even have to look at that here necessarily, because this is just the baseline model. We haven't even constrained those to be equal to each other. So one thing you might want to do is just look at those 3 paths and see, do they look kind of similar to each other or not? You could eyeball it, but that's not going to be how we determine whether we can delete those paths. This becomes my baseline model, and my model 2 is going to be the model that I compare to this model to see if I can actually constrain those paths to be equal to each other, right? Yeah. No, and this fit of this first model is going to be identical, remember, to the fit of my measurement model. So there are no surprises here. It's going to be you're going to have equal degrees of freedom, equal chi-square to the measurement model. And I really don't have to really even look at anything here, but again, you might want to go, if you find out you can't constrain things to be equal, this is the model that you would revert back to see which of those three things you're least likely to be able to constrain. So it does serve a purpose, but at this point, we really don't have to worry about it. Yeah. I tend to constrain them all as a group, and because if that's nice. It's like this multivariate test, and only if things don't look good do I sort of worry about maybe backing out and sort of seeing, is there one that's more problematic than the other? So I would suggest you do them all, kind of like partial measurement invariance, right? Like we do all the constraints at once, and if we can't make all of the constraints, then we can dig in and see, are there, is it everything that can't be constrained, or are there particular things that can't be constrained? But I would start with all of them, because if you can constrain all of them, then you're done, and there's no reason to kind of muck around with all of them sort of separately. Then you just kind of get lost in the weeds. Okay, so 100. I should write this down somewhere. So our chi-square is 100. Okay, great. Excellent. So now our next model, go to model 2. Up. So much, you can just look at the output really. Oops. Where'd it go? I do. Okay, that's model 2. Here it is. Okay, so here's model 2. I'm going to run model 2. Again, I've shown what are the deleted paths, but the first thing I want to do is constrain them to be equal. So look and see, let me show you in the input file how we're constraining those to be equal. Okay, so notice we've got homework on academic self-concept, homework on goals, and GPA on motivation. And so to constrain those to be equal, I'm giving each of them a number, could be a letter, could be a word, doesn't matter. And then I'm going to come down here into model female, and I'm saying homework on academic self-concept 1, homework on goal 2, and GPA on motivation 3. Those are the same numbers I used above. So the fact that I've given, so basically what this number or letter is doing is I'm naming the parameter. That's what I do when I put a number or a name after it. Names are probably better than numbers, by the way, if you're going to go into the constraints and mess with them later, but it doesn't matter for us right now. But so I give it a name, right? And then because I've given it the same name in both sections of my model input file, I'm telling M+ to constrain that parameter to be equal, right? Anytime you give the same name to two different parameters, whether it's within a group or whether it's across groups, that I'm telling M+ to constrain those parameters to be equal. Does that make sense? So here I'm constraining all 3 parameters to be equal. Now I run the model, which I'm not even going to really worry about, and let's go to page 11. Thank you. Page 11. So in page 11, model number 2, I've constrained those conceptually deleted paths to be equal by chi-square. Degrees of freedom. Okay, so clearly not statistically significant, right? Like chi-square is virtually identical, but I picked up. So I can constrain paths to be equal across the 2 groups. Like again, you should always be thinking as you're doing models. I mean, you should be checking your output, but also first thing you do is like check your degrees of freedom, right? I made 3 constraints. My degrees of freedom should go up by 3. Like if for some reason you ran this model and you still got 81 degrees of freedom, you should say to yourself, oh my gosh, I didn't run the model I thought I ran, right? Because, so, but then you say, okay, well, what didn't get constrained that I thought was constrained? Oh, I didn't use the same numbers. I went 1, 2, 3, 4, 5, 6. That was dumb of me. Okay, 1, 2, 3, 1, 2, 3. Now it's going to work, right? So here we go. So obviously I can make those constraints. And because I can make those constraints, the next step is to, yeah, let's see if we can just get rid of those three paths altogether, because I could constrain them to be equal. So my next model is going to go up by how many more degrees of freedom? Well, start with the delete the phone. Up by another 3, right? Oh, we're going to have chi-square equals, I don't know what, with 87 degrees of freedom. Okay. So, how am I going to do that? Oh, yeah, we do need to check if they're statistically significant. Yes, thank you. We do need to check and see if they're statistically significantly different from 0 or not before we delete them. So let's take a look at them. I know what the answer is, but we should definitely look. So, so let's see, on page 14. No, for male. Okay, so I think it's page 12 for male. So we're looking at GPA on motivation is not statistically significant, right? See that? 0.165. And it's not going to be statistically significant in either group because we constrained it to be equal, right? Also, we've got, what were our other two? Homework on academic self-concept and homework on goal, right? And those are also not statistically significant. So yes, thank you. So that's the next thing we have to do. Before we delete them, we want to know, are they statistically significant or not? And the answer is no, they're not statistically significant. So it does make sense to delete them. If one of them were statistically significant, then we would not want to delete that path, right? Most likely. Okay. All right. So the next step is going to be in model 3, we're going to delete those paths. So how do I delete those paths? Well, I just get rid of that out of my code, right? I'm not gonna make reference to those paths in either of my sections of my code. So I just take them out altogether, right? So deleting them is pretty easy. So what does it look like when I delete those paths, those 3 paths that have already been constrained? And now I've got a chi-square with 80. Where is 5, 4? My chi-square difference here is 4.14. And 3. That's statistically. No. So which model do I favor? Third model, right? Because it's not significantly worse. I've made these constraints, so it's a simpler model, but by making it simpler, I don't degrade the fit substantially. So I'm going to favor the simpler model, and the simpler model is the one that has more degrees of freedom, right? So, okay, so we can delete all 3 paths. So that's good. Yay! And it seems like a lot of effort just to get to the point where, right? That's the thing that's a little bit like, oh, okay. You know, it was already kind of a chore to work through all this before with the hybrid model, and now just like extra steps to get here, but we've done it in a logical fashion, and we've gotten rid of our 3 conceptually deleted paths. All right, should we take a break maybe? We're getting pretty late. What do you think? Let's take a break. Let's take a break and come back in about like 10 minutes, and we will finish the rest of these models and then talk about some other stuff. All right, the note I had about max, you need to double check, because this may or may not still be true, but the note that I had about max is that if you make reference to the intercept in the main model, but not in the, not in the subgroup model, that it doesn't actually keep them, it does not default to the scalar model, that it doesn't constrain them by default. So you should check with max and make sure that your intercepts, whatever you do, make sure that your intercepts are constrained by default. That might be again, they might be, they might not be. These are things that change all the time, but that might be a place where the default might be slightly different in a Mac and a PC, but you'll know because you'll be able to see it. If the intercepts are constrained by default, the intercepts that were unstandardized, always look at the unstandardized. The unstandardized intercepts should be the same for males and females, and the degrees of freedom should indicate that they're constrained. If you look on your output and it doesn't look like they're constrained, and you have, right, that you have fewer degrees of freedom, then in that case, then you would need to impose the constraint, right? But I suspect that that might not be the case anymore. Because, yeah, you can check right now. So I think I discovered that back when, because there's also that little hiccup where you can't actually, in the measured invariance, just put this line in, right? Things change all the time. All right. Okay, where were we? So I think we went through the first three models, right? All right. So, and I wrote yes, it's really important to write all of our chi-squares up there. Okay, so now the next thing we would want to do then is actually constrain all of our remaining conceptual paths to be equal across the groups, right? So, and think about what this means then. This is saying, like, is the direct effect of academic self-concept on motivation, right? Or is that sort of parameter, is that coefficient equal across boys and girls, right? So is the effect of academic self-concept on motivation, is that the same for boys and girls? And that's, again, that's the effect after controlling for goal valuation. Is the effect of goal valuation on motivation after controlling for academic self-concept, is that the same across boys and girls? So we're really talking about these, sort of like regression parameters. These are our direct effects. Are they the same across the two genders, or are there differences? And if there are differences, again, this isn't necessarily saying that there are differences in the means on any of these variables across two groups. It's really talking about there are differences in the regression coefficient. So the sort of the predictive strength, right? How well does this variable predict this variable, again, after controlling for other variables? Maybe it's more predictive for boys than it is for girls, or maybe it's more predictive for girls than it is for boys, which doesn't say that boys and girls are different in terms of their motivation or their academic self-concept or the goal valuation, just that sort of our model of predictive pathways, right? Our structural model functions differently across the two groups. So everything that we brought to bear in terms of interpretation of single group models, I mean, we use that same logic, except for that now we're saying, if we can't constrain a parameter to be equal across the groups, we're saying actually, okay, well, this relationship, this whatever kind of relationship it is, predictive relationship, causal relationship, variant relationship, we got all kinds of different parameters, right? But this pathway is stronger in one group than another. Could even be like, you could have something where like maybe the effect is negative in one group and positive in another, right? Or whatever. But that isn't necessarily always the case. Maybe it's just really strong in one group and much weaker in the other. But again, it's not saying anything about means. None of these paths have anything, looking at constraining paths doesn't tell us anything about whether there are mean differences between boys and girls. We're going to look at that too, but we're not, this isn't telling us anything about that. Just about whether our causal pathways or our predictive pathways differ across the groups. Yeah? Okay. So we've got sort of we can think of model 3 now as becoming like the baseline model by which we're going to compare a model where we constrain all of those structural paths to be equal across the two groups, our conceptual structural paths, because we were able to delete all of our conceptually deleted paths. So they're gone, right? So now in our next model, model 4, yeah, this is why I used a number. This is a really good point. And by the way, I don't want to tell you how many years it took me to figure that one out, because I can honestly, I can honestly say I used M+ for a number of years before I figured out I could do that. But I mean, so anyway, but yes, this is a reason that numbers are nice, right? Because I can go like 4 or 5 and 7 through 9. And especially if you've got like a bajillion, if you've got a really big measurement model with bajillions of items, it can be really quite handy. The reason to use words instead of numbers is if you ever are going to use that constraint command. I've never tried it, but I have to assume that it would just get completely confused if you used a number, right? Because you can constrain a parameter to be a number. So I can't imagine, like, it doesn't, I've never tried it, but it does not seem like it, because you could constrain a parameter to be equal to 1, but it wouldn't make any sense to be like 2 = 1, right? Like that, how could that possibly work? It can't work. So that's the reason to use words, is if you're going to actually go in and impose some sort of nonlinear constraints or any kind of constraints in the constraints command, which I don't think we're going to do any of that this semester, not anytime soon. So, but yeah, so this is nice, right? So now I just need to, I'm going to constrain my paths to be equal across the groups. So here I'm saying, okay, motivations regressed on academic self-concept and goal valuation, right? And I'm naming those parameters 4 and 5. Homework is regressed on motivation. I'm calling that 6. and GPAs regressed on academic self-concept, goal evaluation, and homework, and I'm calling those 7, 8, and 9. Right? And then when I come down here, what you're going to see is that what I have to do to constrain those paths to be equal is I basically just have to copy and paste that code into model female. So now I'm saying, okay, for females, motivation on academic self-concept, you know, that parameter 4 is going to be equal to the parameter above, right? It's got the same name, so that means I'm constraining it to be equal. And motivation on goal evaluation, that parameter is named 5. And because I've named it 5 down here and I've named it 5 above, that I am explicitly then saying that they're constrained to be equal, right? So if I put this line here and I didn't put that 4-5 there, so again, this is where you just kind of have to remember what I'm sorry. Trust me, there are worse programs to do this stuff in. Amos is even more of a bear on multiple group stuff, believe it or not. But like, if I put this line in the model female without putting any kind of like labeling of the parameters and giving them the same label, then I'm allowing them to be different across the two groups. It is the process of putting it in this line in conjunction with giving the parameter the same name above and below that constrains them to be equal. Yeah? Okay. Oh yeah, you said that. That's great. Let's just move on because this works too. And I think people are confused enough with all the different people. It works, that's great. But this definitely works. Yeah, like boom, 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 boom. I don't know why. I don't honestly know why that would work, but that's interesting. I'm going to test it after this. But for now, let's just go with what we've got here. Okay. So we're going to run this. Because we've got our output, which is probably easier than scrolling through. So model 4 starts on, I think I made myself, page 28. I made myself a note of what page it started on, actually. So model 4 page starts on page 28. And how many conceptual paths were we constraining to be equal? 6. That's right. There's six conceptual paths that are constrained to be equal. Model 4 has 93 degrees of freedom, 114.7 degrees of freedom. Okay, which makes sense. I went from 87 degrees of freedom to 93 degrees of freedom. So I made 6 constraints. So I picked up 6 degrees of freedom. My chi-square, I think I did the chi-square difference test on page 28. You can see the chi-square difference is 5.63 with 6 degrees of freedom, and that is not statistically significant. So which model do I favor? Yeah, this model where I made the constraints, right? Because the chi-square is not statistically significantly different from the model before. So I'm going to favor this simpler, more parsimonious model because the fit is not statistically significantly worse than the last model, right? Okay. All right. So I can constrain all of these paths to be equal across the groups. Whew, that's good. That makes my job of interpreting them a lot easier. I don't have to interpret them as different across the two groups. Okay, so that's great. Yeah. Yeah, if we couldn't constrain, so I mean that's the question, right? So what if we couldn't? What if it jumped up and we couldn't? And actually, we're going to see that with the means in a second. So maybe I'll show you with the means. It's the same logic that we would use with the paths. Okay, so here we go. Oh, something else I wanted to show you, and I think this is the model where I want to do it. So last week we were talking about computing a Cohen's d, right? So if I wanted to look at group differences, right? What do I do with this model? Let me see. Or the next model. I don't know that it really matters, actually. We'll do it with this model. Okay. So maybe it does model. So just to remind you, remember, when we want a standardized mean numerator, it's the difference between denominator, right? So on a you all clear on this for sure? Full standard deviation. The thing is, if I have my two samples are exactly the same size, or I can just take the two standard deviations and I can average them together to get the full. So I could, if both groups are 200, one is a standard one and one is a standard two, then the average standard deviation. The reality is that we very rarely have two groups that are exactly the same size. So what we need to do is we need to come up with a pooled standard deviation that's weighted by that, like if there are, let's say, 1,000 girls and only 500 boys, we want the girls standard, we want the variance or the girls to have more weight in coming up with a pool than the standard deviation for the boys. That makes sense, right? And in our case, we do have quite a few more girls than boys. So we have, I think, 70 girls and 209 boys. Substantial difference. The pooled standard deviation. Actually, I think I put a slide in this in the PowerPoint too. All it is you're going to do the variance, and you're going to multiply that by the sample size of group one, not total sample size of group one. So like, say the variance for boys, right? Minus the sample or times the sample size for boys minus one. Okay. So plus variance for girls times size for girls minus one. And then, of course, multiplied by the sample size of boys and the sample size of girls, we need to go back and, like, in the denominator, we need to divide by n size for boys plus size for girls minus factor, which if you think of it, is really just this piece denominator. So that now I'm getting back to something that is the variances that are weighted appropriately. I weight the variances, actually. Okay. Only in the case where it's equal can we. And then because to do this, I'm going to get sort of a pooled variance estimate. But for a Cohen's d or a Hedges g, I really want a pooled standard deviation. So after I do all of this, I'm just going to take the square root, and that's going to give me the standard deviation. So in model 4, So in model 4, have 249 boys. So we're going to take 248 times the variance for boys is 0.801. Plus, we have 370 girls, so it's going to be like 369 girls times the variance for girls is 0.463. And where I'm getting these variances is actually, if you look in your output, the unstandardized section, look at the latent variances. Make sure you can find these numbers. In model, let's see, I think I've got it marked down. What page? Page 31. Oh, yeah, I didn't tell you what variable. This is for goal valuation. Sorry about that. So I'm doing this. My example is with goal valuation. So that's the variance right in the middle of page. Then on page 32, the variance and goal valuation for girls right numbers is 0.463. 463. So that's the variance and goal valuation for girls. The variance is, I mean, I don't know, they're kind of different. And we've got variance is not the same. Definitely more girls than boys. So I do all of that. Right? And then I'm going to divide by total sample size minus 2, 17. That's going to be, and then I take the square root of that, and that's going to give me all of that. That the pooled variance actually is 0.59886. Take the square root of 59886. You're going to get 0.774. So the pooled standard deviation is 0.774. Now the question is, okay, well, what's the mean difference between boys and girls in terms of goal valuation? Well, we look at the means for the latent variables, right, for goal valuation. Find them here. So oh yeah, well, I only need to look at the mean for girls, remember, because remember the mean for boys is constrained to be 0. Remember that the latent 0. The latent mean in the second group is actually giving me the difference between boys and girls on that latent variable. So I don't actually even have to do, the mean difference is actually just this number that comes out. The latent mean for girls is actually the latent mean difference. 74. So I take 0.274 and I divide that by 0.774. That gives me 0.35. For which unstandardized values for which piece? I mean, it's all. Well, remember, when you standardize something, you're standardizing it so that like got like the same standard deviation, right? Or standard deviation variance of 1. Yeah. We actually want, I mean, here we want the variances are actually different across the two groups. We need the unstandardized variances, right? Yeah. And yeah, so yeah. So we're definitely using these, we're looking for these means and these variances in the unstandardized solution. So now what I have is again, technically this is really a Hedges G, but I mean, people generally call it like a Cohen's D of 0.354. So this is there's basically about a little over a third of a standard deviation unit difference between boys and girls in terms of their goal valuation. And it favors girls, by the way, because it was positive and girls are 1. So girls report valuing the goals of school more than boys. Their latent goal valuation is about 0.35 standard deviation units higher than boys. You know, again, on this latent variable. It's a latent mean difference. Not observed on a subscale, it's a difference of 0.35, which is, you know, not ginormous, but it's also nothing, right? Makes sense? And this is, I think, really useful. Again, like I said, looking at these values is akin to the t-test. Okay, that's what that 274 is giving me. That's saying there's a statistical difference valuation. And of course, anytime you do a t-test, the next question is, well, I don't know why, but people often get really tough because and they're like, oh, logic. The variance is the latent variable and follows the exact same logic that it always did. Yeah. And you can do this too when you find like if there are differences in the intercept between two groups. You could say like if you want to quantify how big a difference in the intercepts is this, you know, just for an item, you can create something like a Cohen's D. Like, is it a, you know, it might be statistically significant, but is it like a small difference? Is it a large difference, right? So we can always be using, you know, sort of Cohen's D type metrics to be comparing these mean differences on, you know, means and intercepts across the two groups, whether they be measurement, you know, intercepts or structural means and intercepts. Make sense? All right, cool. So yeah, I wanted to make sure, I don't think you have to do anything like that for your homework, but I think it's super useful in the real world. So now, I should probably put it on the homework. I'll do that next year. All right. So okay. So model 4, we were able to constrain all of those paths to be equal. So let's look at the 6 paths that we constrained to be equal. See, so let's look at page 31 and 32, I think, right? Let's see, where is it? 30? 30, here we go, 30 and 32. So, right, so we're constraining motivation on academic self-concept and goal valuation to be equal. Those are both statistically significantly different from 0, though. They're pretty healthy and positive. We're constraining homework on motivation to be equal, and that's statistically significant. We're constraining GPA on academic self-concept to be equal across the 2 groups, and that's statistically significant. We're constraining GPA on homework to be equal, and that's statistically significant. I just skipped over the one that isn't. So let's go back to that. GPA on goal valuation. So right? So this is the path from goal valuation to GPA, which again, we saw this in the single group model way back when. You might not remember that, but the first thing that's weird about this, if you stop and think about it, is that it's negative. So this is actually saying, after controlling for the other variables in the model, the direct effect of how much goal valuation on GPA is negative, which means, again, after controlling for the other variables in the model, the more you value the goals of school, the less well you do in school, which does not make sense. But it is also not statistically significant, right? So it's negative, but it's not statistically significantly different from 0. So yeah, that's kind of wonky and weird, right? So for that reason, maybe I want to get rid of it. It's not statistically significantly different from 0, and it's just weird. So I'm going to get rid of it. Not just, sometimes you get weird results, but this happens to be a weird and non-significant result. So cleaning this up will make me happy. So our next model, model 5, we're going to eliminate that goal valuation to GPA path in both groups, right? We've already constrained it to be equal across the 2 groups, which would be my first step. Now I could eliminate it, right, across the 2 groups. So then how many degrees of freedom am I going to gain here when I delete this path? 1, because I already constrained it, right? And now I'm eliminating it. So it's going to be 94 degrees of freedom. Chi-square. Well, if you look on page 36, the chi-square is, actually, that's not really where the chi-square, the chi-square is on 37, is 115.7. 157, 94 degrees of is that a statistically significant difference? No, it's only a difference of like 1.5 something points with 1 degree of freedom. It's not statistically significant. So which model do I favor? The one where model 5, where I just completely eliminate that path, because eliminating that path doesn't actually substantially worsen the fit of my model. Yes, Katie. No, well, it's the same logic that we were using before. So first we constrain, and then having constrained, is it statistically significantly different from 0? Because if we couldn't constrain them to be equal, we wouldn't want to get rid of it, because the fact that the path is different across the 2 groups is interesting, right? So the first step is, can I constrain the path to be equal across the 2 groups? Yes or no? If the answer is no, then I would argue, you keep it. It could be that it's significant in one group and not in the other group or whatever. That's fine, but I'm going to keep it in both groups because it's different across the 2 groups. And the fact that it's different is interesting, because that would be saying, like, hey, goal valuation, predicts GPA like, again, the direct effect, after controlling for everything else in the model, the direct effect of goal evaluation on GPA is stronger for girls than for boys, or stronger for boys than for girls. So if I can't constrain it, I'm going to leave it in. I'm not going to try to delete it. It's only once I was able to constrain it, and once constrained, I see that it's not statistically significantly different from zero, which, because it's constrained, that's going to be the case across both groups, right? Because it's only one parameter across both groups. And by the way, remember, or maybe you haven't thought about this before, but if I constrain the parameter to be equal across the two groups, my standard, generally speaking, my standard error is going to drop a bunch, because I have a lot more information with which to actually compute that standard error now, right? Before, I had, like, 370 girls and 249 boys. I was like, again, simultaneously estimating a parameter for, this path for girls and this path for boys, right? Well, once I constrain that path to be equal across the two groups, I've got like 600 and some people across so I'm only estimating one path, and I've got over 600 cases to estimate that path. And so the standard error is actually going to drop. So, but, so my standard error is smaller, but it's not which is just an interesting thing. You have more power sort of to detect whether that, because it's constrained, I now have more power to detect whether that constrained parameter is different from zero or not, and it's not. And so I'm totally comfortable getting rid of it. Yes. Yeah, but again, it's true. It was significant for boys, but not girls. But that's not the question. The question is it different for boys and girls? And that was the question I answered when I constrained it to be equal. So I feel like that's like a red herring, looking at the two. I mean, in the easiest way to think about this is imagine there's a line of points. And let's just say that the girls are right here. The boys are right here, right? And so the boys, let's say parameter is statistical, girls parameter is not statistical. But, like, again, this is just some weird and arbitrary line in the sand. The more important thing is, are these two different from each other? And knowing that one parameter is different from zero and another parameter is not different from zero tells you absolutely nothing about whether those parameters are equal to each other. So the first question we need to ask ourselves is, are those parameters equal to each other? If the answer to that is yes, so like here, the answer to this is yes, those parameters are equal to each other, then the next question can be, okay, well, now that I'm only estimating one parameter, is that parameter? That's the lot, and this is, again, it's really important to use logic. Because if you don't, you're going to get tripped up. You're going to find yourself in that kind of space and be like, and get all, but that's not, that doesn't matter that one's significant and one's not. And by the way, one is only marginally statistically significant. The boys, it's like 0.02, right? And the standard error is enormous. And the z-score is like 2, it's just above 2, right? So it's like, it is significant, but it's just like barely crept in there under the wire. Yeah, that's right. And actually, and it's interesting too, because if you look at it, those paths look really different from each other for boys and girls. So, like, it would be really easy to look at that and be like, one's significant, one's not, and the path is really, like, it's almost nothing. It's like almost 0 for girls, and I think it's like 0.5 for boys or something, right? And so they look really different. But the thing is that if you look at the standard errors are really big, which means even though those two paths look different from each other, because the standard errors are really big, that 0.5 is a very noisy estimate of what the path is for boys, right? And so yeah, you can be like, without thinking about the standard errors, you can sort of be, you can get yourself, you can think that that difference is more important than it is, or more meaning, bigger than it is. But the reality is that's a very noisy 0.5, right? And so, and in fact, when I was, looking through these models before today, I thought, yeah, actually, I bet somebody might ask that, right? Like, so what happens if I just constrain just like that, what if I just look at that sort of singly, like, just because remember we took all the constraints together, right? But the reality is that you can just constrain that one path, and it's the chi-square difference is not statistically significant. And it's like, I think the chi-square difference with the 1 degree of freedom is like less than 1. So, but again, so it looks different, but we don't really sort of it's just a very noisy estimate. Or they're both kind of noisy estimates. But the boys estimate is noisier. Again, if you look at the standard error for boys, it's substantially larger than the standard error for girls, and that's because the sample size for boys is, well, there are 2 reasons probably. One is that the sample size for boys is smaller, and it could also be that there's more variance for boys, because for some things there is more variance for boys. So anyway, point is, yeah, so if you use this logic of constrain first and then think about deleting, you won't get yourself in trouble that way. If you don't use that logic, you could end up going down a bad rabbit hole and doing something that actually wouldn't make sense, like getting rid of it in one group and not in another, when in fact that would be a really bad idea. All right. Yeah? How are we doing? Okay. Yes. Mm-hmm. Yeah, I mean, that could happen, right? It could be, now in this case, we were able to constrain all 6 paths, and it didn't worsen the fit of our model. But again, when we get to, I think, when we go to constrain the means and intercepts, we're going to see an example of exactly that, where when we constrain all of the means and intercepts, it does significantly degrade the fit of our model. And so we're going to look at sort of a partial invariance model. So yeah, I mean, if you wouldn't do that, if you do them all as a package and it's not significantly worse, then you wouldn't go back and generally, I don't know why you would, you don't have to go back and sort of like do some sort of post-mortem of that. But if you, let's say you have 15 parameters you're constraining to be equal, all your structural parameters, and the chi-square jumps up by a whole bunch, it could be that all 15 constraints are problematic, or it could be that only one of those constraints is problematic and the other 14 are totally fine. And so, I mean, that's a case where you would probably, just like we did with measurement invariance, you're going to want to dig into partial structural invariance and figure out, are there some I can constrain and some I can't constrain? And for that, to get an idea of which ones are the least likely to be good to constrain, you're going to want to go back to the model before where you didn't impose the constraints and kind of eyeball it. And that'll give you a really good idea of which ones are probably the most likely culprits in terms of, when you constrain it, it makes the chi-square jump. But we're going to do exactly that when we get to the means here for our next models. Okay, so our next question is, okay, model 6. Here we go. So model 6, so we can, we already did, we eliminated the goal valuation to GPA path, but now I want to constrain all of the means and intercepts to be equal across the groups. These structural, I'm not talking about the measurement intercepts here, I'm talking about the structural variables. So think about our model. We have like means for academic self-concept and goal evaluation because they're exogenous variables. But all of our other conceptual variables are endogenous variables. So we're actually estimating intercepts for endogenous variables, which are the like predicted value, right, when everything else is zero. So that's what intercepts are. So if you look at model, well, let's talk about how we do this first. So let's talk about which things we're constraining, and then let's talk about how we do it, and then we'll look at the output. So we have academic self-concept and goals. We're constraining two latent exogenous means, right? We've got two latent exogenous means. We're going to constrain those to be equal. And then we have motivation, which is a latent endogenous intercept. I'm saying intercept because this, we've got academic self-concept, goal evaluation, right? What I mean, both of those things predicting motivation, but motivation endogenous, right? So there's occurrence, right? And so in motivation, we're not actually estimating a mean anymore because it's endogenous. We're estimating, which is like going to be the predicted score on motivation and academic self-concept and goal evaluation are zero. Here we've got a latent intercept because it's endogenous. And then let's see, homework. Those are both observed variables, also have disturbance. Motivation, homework on motivation, GPA on concept, goal, and motivation, but we got rid of. Oh, yeah. That's open too. So anyway, this is the basic idea of it. But now here we also have, so here we have like this variable, but this is also going to be an intercept, exogenous variable. It's also an observed variable. Again, we're estimating an intercept because it's an endogenous variable. So we're always estimating mean. We're only ever estimating means for exogenous variables. We're estimating intercepts for endogenous variables. Just the same way that we only estimate like regular full-on garden variety variance for exogenous variables, but we estimate disturbance variances for endogenous or residual variances. It could be error variance if it's in the measurement part. It's a disturbance if it's in the structural part. Okay. So I've got all my variables there, right? So there are 5 pieces of mean and intercept information that I'm going to constrain to be equal. So I'm going to say, so when I make this constraint as a say on academic self-concept and goal evaluation and motivation, which again are like going to be like the expected means controlling for, right, or holding constant the other variables that are predicting that variable. I'm going to constrain all of these to be equal across the two groups. Does everybody kind of follow the logic of that and what that means?
Can you say that again, Betsy?
Sure. So here, I'm constraining the means of the two exogenous variables to be equal across the groups. So that means I'm just saying like the mean of the latent academic self-concept variable is the same for boys and girls, right? The difference between that and an intercept is that because the intercept is really going to be the predicted or like the expected, let's take motivation. It's like the expected motivation, latent motivation, right? After controlling for or holding constant at 0 academic self-concept and goal evaluation. So we're not testing whether the value of the motivation latent variable differs for boys and girls, because it's an endogenous variable. What we're really testing is, after controlling for academic self-concept and goal evaluation, does that predicted motivation differ across boys and girls? So imagine, like, what would we expect for a boy who's at the average on academic self-concept and goal evaluation? Would we expect his motivation score to be equal to a girl who's at the average on academic self-concept and goal evaluation? Because it's an endogenous variable, that's really what we're testing here. It's not just, are the motivation scores, or not scores because they're latent, but is motivation equal across the two groups, but it's for boys and girls who are equal on academic self-concept and goal evaluation. After controlling for academic self-concept and goal evaluation, is motivation equal for boys and girls? So, like, one way that you could imagine, let's say boys are higher in terms of, I'm just making this up, by the way, right? No, please don't. Let's say boys are higher in terms of academic self-concept, okay? And let's say that academic self-concept positively predicts motivation. It could be that boys' motivation score is also, or latent, so boys' latent motivation is also a little higher than girls, but after I control for the fact that they have higher academic self-concept, boys and girls' motivation is equal. See what I'm saying? Right? Because in this case, evaluation, the same for girls. Like, holding academic self-concept equal across the two groups. So assuming you've got, like, boys are average on academic self-concept and goal evaluation, is their motivation equal to girls who are average? Which is different from just saying, is motivation different across the two groups? Because, like, it could be that if boys are higher on one of these, it could be that if you just looked at motivation by itself, it could be, oh yeah, boys are higher on motivation. But after you control for their level of academic self-concept, then their motivation is like you always have to be careful. Whenever we're talking about endogenous variables, we're always controlling for stuff. So that's really what this is. But it is important to kind of remember that. Not asking the question about motivation different from homework different, homework completion behavior different, GPA different from that's it. After controlling for the variables that predict those things, that's different from what. Let's say you wanted to know the answer. Different from that, because you might want to know that, right? You might want to know this, whether the intercept is different. You might also want to know, just, is motivation different for boys? Question. How would you get that? That means, where would you have to go to compare the mean? Would any of these models give that to you? Any of the models in this packet? Yeah, because in every one of these models, motivation is an endogenous variable, right? So no models in this entire packet would answer that question for you, but don't despair, because you already have the answer from last week. So where would you go? Your measurement model, exactly. So, like, your final measurement model, if you just want to know, are boys and girls different on these variables, you can just go to the final measurement model and just get those simple differences. And so that's a reason why, I talked about how, like, after you do the whole measurement and variance thing, you might want to look at differences in the means across the two groups. And there might actually be a compelling reason in your own research to do both that and this. Because you might want to know, are boys and girls different in terms of their latent motivation? That I go to the measurement model for. I might also want to know, after controlling for academic self, are boys and girls different? That I get from this one. They're both really good questions. They're equally good, and I have the answer both. So this is one of the reasons that I think, there's a lot of good stuff that comes from the measurement model that you might want, even if your end goal is the structural model. You might want to look at the latent means for your latent variables from the measurement model for sort of the same reasons that we like to look at bivariate correlations and we like to look at path coefficients, right? Like sort of two different, we get different information. Okay. I've belabored that enough and we only have like 6 minutes left. So, okay, so let's look at our page 44. If you look at page 44, we need to constrain the means and the intercepts to be equal across the two groups. So how am I going to do that? So if you look at, remember, means and intercepts are always in those brackets. So for academic, self-concept, goal, evaluation, and motivation, those are latent variables. So by default, the way M+ works is it constrains the mean in group 1 to be 0 by default, and it freely estimates the mean in group 2. But what I want to do now is constrain the mean in group 2 to be 0 as well, right? Because, that's kind of the way I need to approach it, is that it's already constrained to be 0 in group 1. Now I need to also constrain it to be 0 in group 2. So if you look at the code under model female, you'll see that the code for the mean, the latent means, looks a little bit different from the way I'm going to approach this for other kinds of constraints. And this is because I've already constrained, I already have a constraint in group 1 where I'm not actually estimating, it's not that I'm estimating a parameter and I'm constraining it to be equal across the two groups, right? That's kind of what I'm doing for all of these other constraint things. But here, the parameters, the mean parameter is for the latent variables constrained to be 0 in group 1. It's freely estimated in group 2. And so now what I need to do, if I want to constrain this to be equal to this, I have to constrain this to be equal to 0 because this is already constrained to be equal to 0. So I can't just say it will not work if you try this. Well, who knows? Never used to. You can prove me wrong. But if you try to say this is constrained to be equal to 0, now I want to constrain this to be equal to this, that's not going to work because there isn't actually a parameter here that's being estimated because this is constrained to be equal to 0. So the only way to really get these two things to be constrained to be equal is to also constrain it to be equal to 0 in the second group. So if you look at the line, the second to last line under model female, it says ASC, again, in brackets, because we're talking about means and intercepts. And this is for the latent variables, because that's the default for the latent variables. Don't have to worry about this with the observed variables of GPA and homework. For the latent variables, I say academics ASC at 0, GOL at 0, and MOT at 0. And I'm constraining those latent means and intercepts to be 0, which they were already constrained to be 0 in the first group. And so by constraining them to be 0, in the second group, I am
Betsy, did you mute yourself?
sorry. Yes, sorry about that. When the mic fell, and so yeah, go ahead. Well, that's true. I mean, that's true that the means here for the latent variables are all 0, although, what does that mean, right? Okay, so does everybody follow that though? So you see how that you got to say the at 0 for that. Now compare that to what I did for homework and GPA. This looks just like the codes that we've been using, right? Because those are observed variables. I can just say homework GPA, again, in brackets, and then I've got the constraints of 9-10, right? And then in model female, I've got in brackets homework GPA and the constraints of 9-10. And that's because for the observed variables, they aren't constrained to be 0 in group 1. So I really can just constrain them to be equal to each other. So you really need to kind of, if it's a latent variable, you're going to approach how you constrain a little bit differently than if it's an observed variable. So we constrain the factor means, I say factor means, it should really say factor means and intercepts to be equal to 0. You constrain the observed means and intercepts to be equal to each other across the two groups. All right, so we do this in our last 3 minutes. We do this, bing, bang, boom, and we get a chi-square of 139.61 with 99 degrees of freedom. So if you look at the chi-square difference there, if you turn to page 45, the chi-square difference is 23.92 with 5 degrees of freedom, and that is statistically significant. So this is a place where we might want to look for partial invariance. So maybe I can constrain some of the means, but I can't constrain means and intercepts, but I can't constrain all of the means and intercepts, right? So like, did all of them? It could be that everything contributed equally, or it could be that there are just, potentially 1 or 2 means or intercepts that are problematic. Now, I think if you go to page 52, this actually is a place where modification indices could help you. And when I look at the modification indices that were printed out here, I notice a few things. First, do you notice that every single modification index that's printed on this page has goal in it? Like, that's a sign maybe something's going on with goal, right? By the way, goal was the variable we used over there when we saw the effect size is not huge, but it's 0.35 is not like nothing either. And then the other thing is where it says means intercepts threshold. So this is the very last line on page 52 before it says title for the next thing. It says 20.566. So that, remember what this is saying. This is saying, hey, you know what? If you allowed the mean for goal to freely vary across the two groups, we would expect your chi-square to go down by about 20.5 points. Well, given that we saw that the chi-square jumped by what, only about 24 or 25 points, and again, this is an approximation, it might not be exactly this, but this is saying, hey, if you let it freely vary, your chi-square is likely to drop by 20.5 points. That to me is a sign that probably the thing that needs to be allowed to freely vary is the latent mean for goal, right? Does everybody follow why I came up with that? So model 7, our final model, which is good because it's 1215, in our final model, I allow the mean of goal valuation to freely vary. So you can see, like in the code there, I no longer am constraining the mean for goal valuation to be at 0. Instead, it's allowed to freely vary across the two groups. And when I do that, now the chi-square is 118.53 with 98 degrees of freedom, right? And the model that we had before that was 139.61 with 99 degrees of freedom. So basically, by just allowing that one mean to vary across the two groups, the chi-square drops by 21 points with 1 degree of freedom. So this model is way better. This is a better model than the one where we constrained all of the means to be equal. But now the other question is it a worse model than the one where none of them were constrained? And so I can compare the chi-square with the 98 degrees of freedom to our chi-square, and if you do that, 4 degrees, actually making 5 degree. That making constraints doesn't significantly. The model that I'm going to prefer is model 7. Not significantly worse than the completely unconstrained model, and it is significantly better than the completely model. Kind of follow that logic? All right, and then right now, but then the last thing we would do is that we could look at could we constrain variances too. I mean, using. That's it. See you next week. Oops. Oops, and I should turn off the recording. Bye, Ethan. I'm waving, but you actually don't have a camera, so you can't see me wave, but I'm waving.
Okay, see ya.
Yeah. Stop recording.